So today, let's decode the amazing world of the solid state. All right, so why should you care about how a bunch of the tiny particles are arranged? I mean, it sounds kind of nerdy, right? Well, it's because understanding this stuff isn't just for a textbook. It's literally the key to engineering our future. That link, that direct connection between a solid's internal structure and how it behaves in the real world, that's where the magic happens. It's how we invent brand new, revolutionary materials. So, picture this. A material that's tougher than steel, but somehow lighter than aluminum. I mean, that sounds like something straight out of a superhero movie, doesn't it? Well, what if I told you that this isn't science fiction anymore? It's real. Yeah, I'm talking about things like carbon nanotubes. They're the ones that can pull off that insane strength-to-weight ratio, and they're set to completely change industries from aerospace to construction. And it's not just them. We're talking high-temperature superconductors, biocompliant solids for way better medical implants, biodegradable polymers, the list goes on. And the key to all of them, it's all about cracking the code of their internal structure. Okay, so to really get how these amazing properties even exist, we've got to go back to basics. We need to look at the most fundamental split in the entire world of solids. You can think of it like a battle, really. It's a battle between perfect, beautiful order and total chaos. And this one difference divides all solids into two huge categories. So, first things first, what actually makes a solid, solid? Well, unlike a liquid or a gas where particles are just zipping around freely, the particles in a solid are pretty much locked into position. They can wiggle and vibrate in place, for sure, but they can't just get up and leave. And that's it. That's what gives solids their rigid shape. It's kind of like a perfectly choreographed dance where everyone knows exactly where they're supposed to be. And this is where we get to those two big families I mentioned. On one side, you have the crystalline solids. Think of them as the perfectionists. Their particles are arranged in this absolutely perfect, repeating pattern that goes on and on throughout the whole thing. We call that long-range order. Then on the other side, you've got the amorphous solids. These are the chaotic ones, like glass or plastic. Their particles are all jumbled up in a big, disordered mess. Sure, you might find a tiny bit of order here or there, but it doesn't repeat. That's what we call short-range order. Now, this difference between order and chaos on the inside, it leads to totally different behaviors on the outside. Take melting, for example. A crystalline solid, like a perfect ice cube, melts at one sharp, precise temperature. Boom, it's done. But an amorphous solid, like glass, it just gets softer and softer and gooier over a whole range of temperatures. That's why people sometimes call them supercooled liquids. But what's even cooler, I think, is this idea of an isotropy. In a crystal, its properties can actually change depending on which direction you're looking. The best way to think about it is like wood grain. It's way easier to split a log with the grain than against it, right? That's anisotropy in action. Okay, so let's zoom in on that crystalline family for a bit. These guys are a huge deal. They make up most of the solids we know, from the salt on your table to the copper in your wires. And it turns out there's a really neat way to classify them. It all comes down to the type of glue that's holding all those particles together in that perfect, orderly pattern. And there are basically four main types of this glue, each with its own special strength. We can think of it like a ladder. We'll start at the bottom with the pretty weak forces holding molecular solids together. Then we'll climb up to the powerful pull of ionic solids. Then we've got the really unique situation in metallic solids. And at the very top, the absolute strongest, the unbreakable network of covalent solids. So what does this look like in the real world? Well, take ice. That's a molecular solid. The bonds are pretty weak, which is why it's relatively soft and has a low melting point. Now compare that to table salt, an ionic solid. Those electrostatic forces are way stronger, making salt hard, but also brittle. You know how it shatters? Then you've got something like copper, a classic metal. It's conductive, you can bend it, that's all because of its special metallic bonds. And then, at the top of the ladder, you have diamond, a covalent solid where every single atom is locked into this crazy strong grid. That's what makes it so unbelievably hard. There's this fantastic description of what's going on inside a metal. It's this idea of an orderly collection of positive ions, just sitting there, held together by a sea of free electrons. I just love that analogy. It's so vivid. You've got these metal ions locked in place, but their outermost electrons aren't tied to any single atom. They're just free to flow around, like a sea, through the entire structure. And that right there, that sea of mobile electrons, is exactly why metals are so good at conducting electricity and heat.
All right, here we go. This is the big aha moment. This is where we take all these concepts, lattices, bonds, order, chaos, and connect them directly to the properties of stuff we can actually see and touch. This is where it all clicks.
So let me ask you this. How can diamond and graphite be complete opposites? I mean, think about it. Diamond is the hardest thing we know of. It's clear and it doesn't conduct electricity at all. Graphite, the stuff in your pencil, is super soft, slippery, black, and it does conduct electricity. And yet, they are both made of the exact same thing, pure carbon. Just carbon atoms. So, what gives? How is that even possible?
The answer, as you probably guessed, is their internal architecture. It's all in the blueprint. In a diamond, every single carbon atom is locked up tight with 4 others, forming this incredibly rigid 3D network. It's like an atomic fortress. There's just no weak point. But in graphite, the carbon atoms form these flat 2D sheets, kind of like layers of paper. The atoms within each sheet are bonded really strongly, but the links between the sheets, they're super weak.
So what does this mean in the real world? Well, that 3D fortress structure is what makes diamonds so incredibly hard. And graphite? Those weakly connected layers can just slide right past each other. That's why it's soft and slippery. It's literally leaving layers behind on the paper when you write. And get this, there's a bonus. In graphite, there's a free electron hanging out between those layers, and since it's free to move, bam, graphite can conduct electricity. It's amazing, right? The exact same element, just a different blueprint, gives you completely different material.
Okay, so we've established that structure is everything. It's the blueprint. So how do scientists actually talk about and describe these blueprints? To wrap things up, let's look at the fundamental framework that nature uses to build every single one of these amazing crystalline solids. It's a concept called the crystal lattice.
Now, a crystal lattice isn't the atoms themselves. This is the key thing to get. It's more like an invisible, abstract scaffolding. It's just a pattern of points, repeating over and over again in 3 dimensions, that shows you where the atoms or molecules are going to be placed. That abstract scaffolding analogy is perfect. It's the invisible grid that the entire crystal structure is built on.